Hello, everybody, and welcome to the Latin American webinars of physics. Today, welcome to, we hope that you have a very nice holidays. And we're gonna restart with the webinars in this 2023. Our first speaker of in this year is gonna be Valentina de Romeri. She's a postdoc in the Instituto de Física Corpuscular in Valencia, Spain. But before, she has done a lot of work in different topics related with neutrinos, beyond standard model, dark matter, and neutrino physics. And so again, and in the past, she got the PhD from the Universidad de Valencia and the Universidad del Instituto di Torino in Italy. After that, she have done several postdocs in the European network Invisibles. She has also been postdoc in the IFT in Madrid, in the UAM. Also, she got the Juan de la Cierva Incorporación, a postdoc position to be done in Valencia. And lately, she is a research CEvNS from Valencia, Spain. And after that, she's going to be a distinguished researcher in the CEvNS, also at IFIC. So, Valentina, welcome to the lawphysics. Please, you can start your webinar and share your screen.
Thank you so much, Roberto, for the introduction. Hello, everyone. So let me share my screen. Can you see the presentation?
Yes, perfect.
Okay, so first of all, I would like to thank you for this invitation. I'm really happy to participate in these lawphysics webinars. And in my talk today, I will discuss coherent elastic neutrino-nucleus scattering in the standard model and beyond. This is the outline of the talk. I will start with a brief introduction and motivations behind the coherent elastic neutrino-nucleus scattering process, also called CEvNS. And in particular, I will discuss the observation of CEvNS at experiment Coherent and the recent evidence for a possible observation of CEvNS at a reactor experiment using neutrinos from the Dresden 2 reactor. Then I will comment about some of the extended physics potential of CEvNS, both concerning standard model precision tests and the searches for new physics, for instance, in the form of new interactions in the neutrino sector. In the second part of the talk, instead, I would like to discuss CEvNS as a background for dark matter searches. In this case, I will comment about the impact of these recent CEvNS measurements on the so-called neutrino floor. And finally, I will summarize. So the coherent elastic neutrino-nucleus scattering process is a neutral current process in which a neutrino scatters off a nucleus via the exchange of a Z boson. And the neutrinos in this process sees the nucleus as a whole, as a single particle. This process occurs when the momentum transferred in the process is smaller than the inverse of the nuclear radius. This means that there is an upper limit on the incoming neutrino energy of the order of about 100 MeV, depending on the target material. And this makes that the nucleon amplitudes sum up coherently, and it leads to a cross-section enhancement. So the CEvNS cross-section turns out to scale approximately with the number of neutrons squared, and eventually this cross-section can be quite sizable, for instance, a couple of orders of magnitude larger than the inverse beta decay process, which was first used to observe neutrinos. This process was first theoretically predicted in the 70s. However, it had eluded detection during more than 40 years because it is an exceptionally challenging process to observe. Indeed, despite the magnitude of its cross-section, it was not observed for so long because it gives rise to very tiny nuclear recoil energies. And so this makes the detection quite complicated. In this plot on the left, it is shown the typical magnitude of the CEvNS cross-section in blue compared to other neutrino cross-sections. For instance, in red, there is the inverse beta decay one. In the plot on the right, instead, it is shown the typical n-square dependence of this cross-section. And also, there are depicted the measurements of this cross-section by the coherent experiment, which used two different targets, cesium iodide first and then argon. And also there are shown some upper limits on this cross-section, which have been set by other CEvNS experiments using reactor neutrinos, and also by their Mediators experiments observing astrophysical neutrinos, in particular solar neutrinos. There is currently really a worldwide effort in order to observe and measure this process with different experiments, and many of them are shown in this map. So I will discuss in particular about Coherent, which I've said, as I've said before, it's the first one that has observed this process. And also I will comment about this experiment using neutrinos from the Dresden 2 reactor. As you can see from this map, basically Coherent is one of the few experiments which use neutrino from stopped pion beams. I will discuss this more in the next slide. Most of the other experiments currently running or planned in the near future instead would use neutrinos from nuclear reactors. So talking about neutrino sources for these CEvNS experiments, let's see which are the preferable requisites that these sources should have. So first of all, a high flux, a well-understood spectrum, possibly the possible production of multiple neutrino flavors, also the possibility of locating the detector close to the source, and also a good knowledge of backgrounds in order to reject most of it. So as I was saying before, Coherent uses neutrinos from PIDARs, pion decays at rest, and in particular, Coherent uses the spallation neutron source, in which a proton hits a mercury target, and here pions are produced. The negatively charged pions are captured right away by the nuclei, whereas the positively charged ones decay at rest, producing a prompt flux of muon neutrinos and delayed fluxes of electron neutrinos and muon antineutrinos. So the typical fluxes of neutrinos produced from PIDARs are shown in this figure. Most of the other CEvNS experiments instead uses neutrino from nuclear reactors, and in this case, the typical flux is shown in this other figure on the left. And so there are some differences among these sources. First of all, the source of neutrino from nuclear reactors produces a single flavor because only electron antineutrinos are produced. Also, the fluxes at reactors are usually higher, and the energies are smaller. So also the recoil energies which are produced are usually even tinier. And this makes the detection at CEvNS experiments using reactor neutrinos even more complicated. There are a few other possible neutrino sources which have been considered in the literature. However, I will not discuss them in this talk. Talking instead about detection strategies, well, you will understand right away that since these experiments need to see very tiny recoil energies, basically they have the same need like their Mediators direct detection experiments, and also the detection strategies are therefore in common. So these experiments can see, for instance, light. They can see photons if they rely on scintillation as a detection strategy. And this is the case, for instance, of the Coherent experiment. Or they can see ionization. And this is instead, for instance, the case of the Dresden 2 reactor experiment. Or they could also see phonons. This table summarizes some of the experiments which I've shown before on the map, which are currently running, and the technology which is used for the detection, where the location and the neutrino source. So as I was saying before, Coherent is one of the few that uses PIDAR neutrinos, whereas most of the others use reactor neutrinos. And at the moment, the only observation has been made by Coherent, and there was this claim for a possible evidence of an observation also by the Dresden 2 reactor experiment. But I will comment more about both of them soon. So the first observation of CEvNS was made by this experiment Coherent in 2017. So I recall here this was done about 40 years after the first theoretical prediction. And this experiment observed CEvNS first using a detector made of cesium iodide. Then more recently in 2020, they repeated the detection using a different detector made of liquid argon. And in 2021, at the end of 2021, they also increased the statistics of the first detectors, the cesium iodide one, and also they improved the data analysis. So in the following, I will show some results which we have obtained analyzing these data from Coherent. In particular, I will focus on these two data sets, the liquid argon and the most recent one using cesium iodide detector. Concerning the reactor neutrino experiments, last year there was this claim by this experiment, which is actually very interesting, of a possible evidence of an observation of CEvNS. So this experiment uses neutrino from the Dresden 2 reactor in the US, and the detector is a germanium detector characterized by a very low energy threshold. So in this paper from last year, they claim this suggestive evidence of CEvNS, which is reported with a strong preference with respect to the background-only hypothesis. However, the interpretation of these results in terms of a possible observations of CEvNS in the standard model is actually very strongly dependent on the quenching factor model. The quenching factor is a parameter which is very relevant because it describes the observed reduction in ionization yield produced by a nuclear recoil when compared to an electron recoil of the same energy. And this quantity is often not well known at low recoil energies. So it's a major source of uncertainty for these experiments. So as you can see in this plot on the right, the plot shows the values for this quenching factor as a function of the nuclear recoil energy. And the shaded areas are those that have been probed by these two CEvNS reactor experiments, CONUS, and this experiment using the Dresden 2 reactor neutrinos. So as you can see, there are also three different curves, let's say, that correspond to three different theoretical models for this quenching factor. So within the shaded area, the differences are not so large, I mean, at least among two of them. But if we extrapolate them at very low energies, we see that the expected value can be very different. So, well, this is to make the point that indeed the quenching factor is an important source of uncertainty, and this interpretation of these experimental results in terms of an observation of CEvNS strongly depends on this model. But let me now go back to the theory of CEvNS, and in particular, I would like to discuss now the CEvNS cross-section, because this cross-section is actually well calculable in the standard model, and in full generality, it contains two ingredients, two components, an axial one and a vector one. However, the axial contribution is in general small for most nuclei, in particular the heavier ones. It is spin dependent, and therefore we can actually safely neglect it. Also because the typical n-square dependence, which gives rise to this typical enhancement of the cross-section, actually comes from the vector part. So let's focus on the vector contribution to the cross-section. So here the relevant ingredients are the Fermi constant, a kinematics term, the nuclear force factor, which encodes the distributions of nucleons inside the nucleus, and it is approximated to 1 in the case of full coherence. This means when the momentum transfer goes to very small value. And then we have this weak nuclear charge, which is the quantity which eventually encodes the typical n-square dependence. Indeed, within the standard model, this is the expression for this weak charge, and we see that there is an accidental cancellation due to the value of the weak mixing angle in this term that multiplies the number of protons. So it turns out that it's the neutron contribution that dominates, and this is the quantity that leads to the typical n-square dependence of this cross-section. The observation of CEvNS has really opened the window to a plethora of possibilities of physics tests and probes, both concerning standard model precision tests, the study of nuclear physics properties, the study of supernova and solar neutrinos, but also probes of the existence of new physics, for instance, new neutrino interactions like neutrino NSI, the probes of neutrino non-trivial electromagnetic properties. Also, the existence of sterile neutrinos can be probed with CEvNS. And as we will see in the second part of the talk, CEvNS is also a relevant background for their matter searches. So in this talk, I will try to discuss a few examples among these really many applications of CEvNS. Let me start with the standard model precision test, and in particular, CEvNS can be used to determine the value of the weak mixing angle at a low energy scale. So this parameter is usually determined, measured at heavier energies through collider experiments. However, CEvNS can give us information about the value of this standard model parameter at lower energies. These two figures have been taken by these references, which analyze the first data set from Coherent of 2017 and the liquid argon one, and extracted some best fit value for this weak mixing angle, which are shown here in this plot on the right in green. This plot shows the running of the weak mixing angle as a function of the energy scale. And here I am also showing the best fit values together with the error band that we obtained by analyzing these recent Dresden 2 reactor data. I'm showing two of them because, as I said before, these results depends on the quenching factor model. So we chose two different theoretical models in order to see the difference. And as you can see in one of the cases, the error bar is still quite large. This other plot down here instead shows prospects for the determination of this parameter at a future scintillation bubble chamber experiment using a liquid argon detector and reactor neutrinos as a source. We have updated these results for the determination of the weak mixing angle, analyzing the most recent data from Coherent together with the liquid argon dataset. And these results are shown here on the left in terms of this delta chi square, and on the right again as a function of the running of this weak mixing angle as a function of the energy scale. So this is the result that we obtained from the combined analysis of the two data sets, and this is compared to the orange line, the orange curve, which is the theoretical prediction, because of course we can predict the value of the weak mixing angle at low scales by the RG extrapolation. However, it is also important to confirm this experimentally, because any possible deviation from the predicted value would be a clear hint for the existence of new physics. Still continuing with the standard model precision test, CEvNS can be used to probe the neutron density distribution. So contrarily to the proton density distributions, which are better known, the neutron one is not very well known, and therefore CEvNS can be used to provide a model-independent measurement of the so-called root mean square neutron radius, which is a quantity which enters the nuclear force factor, and it is relevant therefore for the calculation of the CEvNS cross-section. Basically, CEvNS can give us information about the so-called neutron skin, which is defined as the difference between the neutron and the proton radii. So also analyzing the two data sets of Coherent from cesium iodide and liquid argon detectors, we obtained some 1 sigma preferred ranges for the values of these radius for the two target materials. Okay, so these were examples of possible precision tests within the standard model, but actually CEvNS is also a very powerful tool to probe the existence of new physics beyond the standard model. And the first case that we considered are neutrino NSI, neutrino non-standard interactions, which are in general formulated in terms of an effective dimension 6 4 fermion Lagrangian of this kind. Where these epsilons are the NSI parameters, which give the strength, the magnitude of this NSI in terms of G Fermi. And this epsilon can be either flavor preserving or flavor changing. So we have analyzed, again, these Coherent data, assuming the presence of, in this case, flavor preserving NSIs. And this plot shows our results. So the lower panels correspond to the electron neutrino flavor NSI parameters, whereas the lower ones to the muon one. And the plots on the left show the results for the analysis of the two data sets separately, whereas the plots on the right show the result of the combined analysis. So the first thing that we can notice is that in the case of the electron flavor, if we analyze the two data sets separately, we get one single band and not two different ones, as we actually we would expect. So why two? Because one of them contains the 0,0 result, which corresponds to the standard model case, and the second band correspond to the values of the NSIs, which mimic perfectly the standard model contribution. So in the case of when we analyze the two data sets separately, in the case of the electron flavor NSIs, we don't get these two bands because, well, the electron neutrinos are subdominant in the flux, in the neutrino flux used at Coherent, and therefore data are not enough to lift these degeneracy. However, when we combine the data sets, we get the two bands as expected. In the case of the muon flavor, instead, muon neutrinos are more sizable in the neutrino source of Coherent, and therefore we get the two bands already here. And of course, when we combine the data sets, the results, the bounds are even more stringent. Similarly, we have analyzed also the case where these NSIs are flavor changing, and now here our constraints are given in terms of one flavor changing and one flavor conserving parameter, again for the electron and the muon flavors. And as before, well, we get that when we combine the data sets, the results, of course, are much more stringent. Neutrino NSI are actually one possibility, let's say, of these new neutrino interactions, in that case mediated by a vector particle. However, one could consider a more extended set of new interactions, which we would call neutrino generalized interactions, NGI. And this can include all additional types of Lorentz invariance interactions. In this case, we focus all on scalar and tensor terms. In principle, we could have also pseudoscalar or axial interactions, but as in the case of the standard model, this would lead to subdominant interactions. And so we decided to focus only on the scalar and tensor terms. And in this case, the effective Lagrangian for this NGI is given by this expression. So now, instead of having the epsilons of the NSIs, we have these equivalent, let's say, parameters, which are called C. Also, these NGI could be present separately, one at a time, or more than one could be present at the same time. So we perform two different analyses. In the first cases, we assume the presence of only one NGI at a time. In the second case, we assume the presence of two different NGIs. So these plots show our results from the analysis of coherent data. The upper panels correspond to the analysis of one single NGI at a time, a scalar one, a vector, or a tensor one. And well, in this case, the results are given in terms of reduced chi-square profiles, again, for the two data sets separately and for a combination of them. So as we can see, basically the combined analysis is almost fully driven by the cesium iodide dataset, which contains more statistics. And in the case of the vector NGI, which would correspond to the NSI case, basically, we get two minima as before we were getting the two separate bands. The lower panels instead correspond to the second analysis, where we assume the presence of two different NGIs at the same time, a tensor and a scalar one, a scalar and a vector, or a tensor and a vector one. And also in this case, well, the combined analysis is dominated by the cesium iodide dataset and leads to quite stringent constraints in this 2D parameter space. And in this case, also to two different regions, which again correspond to the two minima in the for the vector NGI. Okay, so both the NGI and the NSI are effective interactions which assume the presence of a new mediator, which is a heavier particle. However, we could consider, motivated by some theory arguments, we could consider new interactions mediated by light particles. And we could start with the light vector mediator. So in this case, our CEvNS cross-section would be modified in this way. Now, the relevant thing is that, of course, we have now a dependence on the mass of this mediator. We have to make some simplifications, some assumptions if we want to show our results in terms of a single coupling and the mass of the mediator, because in principle, well, we have more free parameters, but we are assuming that this mediator couples equally to the quarks and to the neutrinos in a universal way, okay? This is our assumption that allows us to show the constraints in this parameter plane. So the blue contour shows our 90% confidence level constraints from the combined analysis of the cesium iodide and the liquid argon coherent data. And we see that we get this weird region here, which is a region where we have a destructive interference between this new light vector mediator and the standard model contribution. In this plot, I'm also showing other constraints which apply to this parameter space from other experiments, other kind of experiments or observations, and other CEvNS experiments using reactor neutrinos like CONUS and CONI, which have not observed yet CEvNS, but they have published results setting some upper limits on the CEvNS cross-section. In the plot on the right, instead, we show the same, the limits on this coupling and the mass of the light vector mediator, but from the analysis of the Dresden to reactor data. So we see that at very low masses, the bounds are, let's say, almost comparable, but around, let's say, 1 MeV, reactor data do better, and the constraint is a bit more stringent than the coherent one. Similarly, we could consider also a new interaction mediated by a light scalar particle. And so in this case, our constraints are given in terms of the coupling of this scalar mediator and the mass of the scalar mediator. And also in this case, we get, actually in this case, we get the reactor data leads to more stringent constraints compared to the coherent ones. So another BSM scenario that one can study using CEvNS is the so-called sterile neutrino dipole portal. And here we're assuming the possible transition of an active neutrino to a massive sterile state induced by a magnetic coupling given by this Lagrangian. So here lambda in general is a matrix, a 3 times n matrix. If we assume only one sterile state, it's a 3 times 1 array basically. So we have an upper limit on the mass of the sterile state that can be produced, which is dictated by kinematics and depends on the energy of the incoming neutrinos. And the CEvNS cross-section for this scenario is written here, so it's a bit more complicated, but it can be expressed in terms of an effective magnetic moment, which eventually encodes entries of this lambda matrix and entries of the neutrino mixing matrix. So our results are given in terms of this effective magnetic moment and the mass of the sterile state. Again, I'm showing here two plots for the analysis of coherent data on the left and the analysis of the Dresden 2 reactor data on the right. Also in this case, reactor data lead to a bit more stringent results. However, it is interesting to notice here the complementarity between these two experiments, because the reactor experiments are only sensitive to the electron neutrino flavor, whereas with coherent we can also constrain the muon one. And so even if it is a bit less stringent, it provides an information that cannot be extracted using reactor data. Finally, another possible BSM scenario that can be studied with CEvNS is that of sterile neutrino oscillations. So, as I said before, CEvNS is a neutral current process, so it is sensitive to the total flux, the total neutrino flux. So, one can study the possible oscillation of the active neutrinos into sterile ones. In this case, what we would observe would be a depletion in the flux, let's say, due to these oscillations. So we can perform an analysis introducing these probabilities of oscillations of active into sterile neutrinos. And in this plot, I'm showing the results, the constraints that we obtained analyzing coherent data in terms of the mass splitting and the active sterile neutrino mixing angle. However, this scenario actually does not lead to a good fit of this coherent data, and therefore the sensitivity to this new mass splitting and the active sterile mixing angle is still rather poor. However, it will be possibly improved with future CEvNS data. Okay, now in the second part of the talk, I would like to discuss CEvNS as a background. So now, until now, I've shown some possibilities of what we can do using CEvNS data, both in probing the standard model or the existence of new physics. But now in the second part, I would instead like to discuss CEvNS as a background for dark matter searches. So, well, we all know that if dark matter is in the form of particles like WIMPs that interact among themselves and with the standard model particles, then one of the strategies that has been envisaged to detect it is direct detection, which looks for the energy deposited within a detector. In this case, we are interested in the dark matter nucleus scattering. So this plot shows the current status of spin-independent WIMP nucleon interactions in terms of the spin-independent cross-section and the WIMP mass. And as we can see, there are many experiments that have already probed and constrained a large region of this parameter space. And these experiments are expected to improve furthermore in the near future by probing lower WIMP masses, thanks to lowering the energy thresholds, or also probing smaller cross-sections by increasing the exposure and lowering the backgrounds. So soon, these experiments are expected to hit an irreducible background generated by astrophysical neutrinos. Indeed, there are some astrophysical neutrino backgrounds which will affect these direct dark matter detection experiments. And so this plot shows these fluxes for these astrophysical neutrinos from the sun, the atmosphere, and the diffuse supernova neutrino background. This is a cumulative flux of neutrinos produced from the core collapse explosions of supernova along the whole history of the universe. So we see that these fluxes, especially at low energies, the solar ones, can be quite sizable. We can compute the expected recoil rates from these astrophysical neutrinos inducing CEvNS on the targets of these dark matter direct detection experiments. For instance, here we chose xenon. And we see, well, these are the individual recoil rates for the different neutrino sources and the total one. It is interesting to superimpose on them the expected rates from a WIMP scattering in the same target material. And we could see that a WIMP with a mass of around 6 GeV could mimic pretty well the expected rate from boronate solar neutrinos, whereas a heavier WIMP with a mass of 100 GeV could mimic the expected rate from atmospheric neutrinos. So these astrophysical neutrino backgrounds will induce CEvNS in these detectors and produce nuclear recoil spectra, which can have a strong degeneracy with those expected from spin-independent WIMP interactions. So increasing the exposure of these experiments will not imply a linear improvement of sensitivities, but rather will lead to a saturation of the discovery limit, which is what is typically referred to as a neutrino floor. Actually, more recently, people have started to talk about neutrino fog because we should not see this background as a hard limit. But, well, first of all, it depends on several uncertainties. For sure, there are astrophysical uncertainties affecting the distribution of dark matter. But there are also nuclear physics uncertainty, which affect both the scattering of neutrinos and WIMPs in the detector, uncertainties affecting the neutrino fluxes, which can be quite relevant, and also the possible existence of new physics in the neutrino sector. Moreover, this background can be in principle overcome, for instance, with measurements, detailed measurements of the WIMP and neutrino recoil spectra tails, or also with other techniques, for instance, using different target materials and so on. What we wanted to do here was to try to use the information that we can extract from these recent CEvNS measurements and see how these can affect the WIMP discovery limits. So first of all, let me define a discovery limit. This is defined as the smallest WIMP cross-section for which a given experiment has 90% probability of detecting a WIMP signal at least 3 sigma. So this is the definition that is usually considered for the determination of these WIMP discovery limits. To obtain the discovery limit, this follows we usually follow a frequentist significance test using a likelihood ratio as a test statistic. And this profile likelihood ratio corresponds to a test statistic against the null hypothesis, in which we assume only the CEvNS backgrounds from the astrophysical neutrinos, versus the alternative hypothesis, in which we assume the CEvNS background plus the WIMP signal. So we have to define a likelihood, which is shown here. And here the assumptions are that the number of events, the expected and observed ones, follow a Poissonian distribution, whereas the uncertainties, for instance, on the neutrino flux normalizations or the astrophysical uncertainties affecting the dark matter distribution, follow a Gaussian distribution. So this is the typical method which is followed to obtain these WIMP discovery limits, and we follow it the same, but we wanted to extend it, including some extra uncertainties which could affect these determination of the discovery limits. For instance, as we have seen before, the value of the neutron radius is still a bit uncertain, and so an uncertainty affecting this parameter could change the discovery limits. Similarly, also the value of the weak mixing angle, if we want to rely only on the value determined experimentally by the CEvNS experiments at low energy scale, also is still affected by some uncertainty. However, the first analysis that we wanted to do was one that we called the data-driven analysis. Here we wanted to use the measured CEvNS cross-section and encodes all possible uncertainties that this cross-section could involve within an uncertainty on the cross-section itself. So this would be independent on any assumptions. So what we did here was to extract the value of the cross-section, the CEvNS cross-section from coherent data together with the standard deviation. And then we weighted the theoretical standard model value of the CEvNS cross-section by a multiplicative factor that we obtained from this experimental data. This multiplicative factor is obtained as a ratio between the measured number of events over the theoretical expected ones. And these two plots shows the value of this multiplicative factor as a function of the energy beams, which are given by the experimental collaborations, on the left for the cesium iodide dataset and on the right for the liquid argon one. So using this information, we recomputed the WIMP discovery limits, and these are the results that we obtained for, on the left, we are assuming a xenon detector, and on the right, an argon one. Of course, in the case of the argon, we can use the information from the liquid argon data of Coherent directly. In the case of xenon, we are using the information from the cesium iodide dataset because, well, the mass number is very similar, so we can do that. Our discovery limits are, of course, given in terms of the spin-independent cross-section and the mass, the WIMP mass, and we show them for 4 different values of exposures. So the plain lines correspond to the standard case, where we obtain these discovery limits calculating the CEvNS cross-section theoretically within the standard model, whereas the dashed lines are obtained when we allow for this variation of the CEvNS cross-section within the uncertainty that we have extracted from coherent data. So what we can see in the plot on the left is that when we use the coherent data, the cesium iodide coherent data, we get in general an improvement of the discovery limits. Why? If we go back here, we see that in this case, this multiplicative factor is almost always smaller than 1 in almost all bins. This means that the experimentally measured CEvNS cross-section is smaller than the theoretically predicted one. So we are, if we use the experimentally measured one, we predict less CEvNS events, less backgrounds, and the discovery limits improve. In the case of the argon data, the situation is the opposite. Of course, here the statistics is much less, so there are only 3 bins, but the situation is basically the opposite, and that's why we have a slight worsening of the discovery limits, but the effect is much less pronounced compared to the cesium iodide case. Okay, then another kind of analysis that we did was instead to see what was the impact of an uncertainty on the weak mixing angle value on the discovery limits. So here we allowed for a variation of this parameter within 10% uncertainty, which is the one that we extracted from coherent data, basically. And we see that the impact of this variation on the discovery limits is basically only visible here in this region, which is where the high fluxes from solar neutrinos are sizable. And the effect is that the discovery limits get slightly worsened. And this is because when this weak mixing angle value gets larger, then also this weak charge, which entered the CEvNS cross-section, if you remember, becomes larger, and therefore we are predicting more background events. Another possibility that we considered was the impact of an uncertainties on the nuclear form factor. As I said before, the value of the neutron radius is still uncertain, so we assumed a possible variation of 10% of this parameter, which enters the nuclear form factor. And in this case, we get that actually the effect on the discovery limit is milder compared to the previous case, because actually this affects not only the CEvNS background, but also the WIMP signals. Okay, then also another possibility that we considered was the possible presence of new physics in the neutrino sector. So as we have seen before, the possible existence, for instance, of a light vector mediator. So we consider this case, and we see that in this case, the impact is actually very large, especially at masses, at WIMP masses below 10 GeV or so. What we get here is that the discovery limits get much worse. And this is because when we go to low WIMP masses, or this is equivalent to go to low recoil energies, this new vector interaction is very relevant and adds on top of the standard model contribution. So we predict much more background events, and therefore the discovery limits are much worse. If we go at heavier masses, instead the situation gets reverted, because what happens here is that basically here this would correspond to heavier recoil energies. The vector contribution becomes smaller, and since there can be a destructive interference, because actually the weak charge of the standard model is negative and this is positive, they can cancel, and that's why at heavier masses instead the discovery limits improve. Also, we consider the case of possible presence of a light scalar mediator, and similarly to the previous case, at low WIMP masses, basically the effect is that the discovery limits get worse. And at heavier masses, also, these are a bit worse, but I mean, the effect is much less pronounced. Here, it is not possible, the interference, because there is a chirality flip. So the two, this new interaction cannot interfere destructively with the standard model. However, here, basically, the contribution from this new light scalar mediator is much smaller, and that's why the effect is almost not visible on the discovery limits. So I think that with this, yeah, I've come to my summary. So in my talk, I've discussed the coherent elastic neutrino-nucleus scattering process. At the beginning, I introduced this process. In particular, I highlighted the coherence condition and the typical enhancement of the CEvNS cross-section. Then I have discussed some of the extended physics potential of CEvNS, both concerning standard model probes and probes of new physics. I've presented some results analyzing recent data from the Coherent and the Dresden 2 experiments. And in the second part of the talk, instead, I've discussed the application of these results on Dark-matter searches, and we have reconsidered the possible variation of the so-called neutrino floor, exploiting these CEvNS measurements by the Coherent experiment. So I think that the take-home message from my talk should be that while this process is very interesting and there is a wealth of information also expected from forthcoming data, and these will have very relevant implications for both tests of the standard model and searches for new physics in the neutrino sector. If you let me 1 minute more, I would like to make some shameless promotion of a new project that we have just started at IFIC, which is a physics podcast for the general public, and it's in Spanish. So I thought that maybe among the listeners of the law physics webinars, there could be some people interested. So it's, yeah, as I was saying, it's a new project, which we have just started. It's for outreach, I mean, for the general public. You can find us on all the major podcast platforms, also on Twitter. So if you are interested, or you know someone that could be interested, please share the words. And also we count on, we will count, I hope, with the participation of many people from the law physics community, because while in every episode we have an interview from some famous physicists. So we hope to get the chance to interview also many of you. So thanks a lot. I'm ready to take questions now.
Thank you very much, Valentina. So, and please, all the people that is following the webinar, also join the oscillator armónico, just to also to spread the word about physics. So thank you very much, Valentina. It was very interesting, your talk. So we are going to start with some questions. We have maybe some questions from the people here in the Zoom session. I don't know if some of you guys has questions. Nicolas has one question. Please.
Thank you, Valentina. Very nice talk. So I got confused with your slide 33, I think. If you could please go back there.
Yes. This one?
Exactly. So, yes. So, so the lines correspond to different neutrino fog background? No.
Yes, these are different discovery limits. Sorry?
Okay, so that's like how deep the detectors can go, right?
Exactly, yeah.
But then why the two xenon, I guess when you have xenon 1 ton correspond to the current limits. Why are they different?
They are different. You mean the gray one?
Exactly.
The gray area.
Mhm.
I don't think they are different. It's different the
The Y
yes, the
axis.
axis the axis range.
Okay, yes.
Yeah,
Okay,
I mean,
yes.
this is shown, I mean, of course, would apply in this case directly. I mean, it's shown more, these limits is shown just for reference, let's say.
Yeah, okay. So
But
yes,
it's a
that's why
different
I was confused.
range, yeah, y-axis range. Probably it's that confuses.
Okay, yes, thanks.
Mm.
And if I may, at the very beginning, also, when you explain the quenching factor at the very beginning, I think it's slide like 10 or 11.
Here?
Exactly, yes. So I mean, we expect, for instance, the blue and the black, I mean, at the beginning, or if you want, at high nuclear recoil energies to be the same, right? So that's kind of normal. But the green one is super different. Why? They were not, I mean, I expect the three to be very, very similar.
Yeah, the green one is a different. Yes, that's right. I don't know exactly why, what are the reasons behind. I mean, I know that these two ones, the blue and the black ones, I think they are extracted more experimentally, and instead the green one comes from a theory also. I mean, it has a theory, let's say, motivation behind. But I cannot right now tell you exactly why they are so different, also at heavier energies.
Because they're kind of parallel. It's just like an overall factor. Okay. So maybe the difference could be like associated to the uncertainty of the model or whatever. Yeah. Okay.
Yeah,
Thank you.
could be.
Okay, thanks for the question, Nicolas. And before to continue with the question from the people here in the Zoom session, we have a question from the YouTube channel from David Cardona. He's asking, what are the usual nuclei used in this kind of experiment? I guess also to see this.
In which in the
xenon and other type, if there are more nuclei that can be used for this kind of.
For the CEvNS, you mean CEvNS experiments?
Yes.
Yeah, like germanium, well, cesium iodide, which was used by Coherent, for instance, argon. These are some, in general, the heavier ones, because since they want to exploit this n-square dependence, the heavier ones, the enhancement is larger. So.
Okay, that was the question from David. So I don't know if there are other questions from the. Joel has a question.
Yes. Could you go to slide 20, please?
Yeah.
Right. So in this fits are very nice, and there you can see the effect that you were mentioning on the. For example, let's talk about the vector interaction, right? So there you see what you mentioned before, right? That you have the solution that that is a standard model case, and then another one that mimics the standard model. So in how does it mimic the standard model result? In what way does it give you the same thing?
Yeah, basically it modifies this weak charge that I show. Okay, this is the new definition of the weak charge in this NSI case. Similarly for the NGI, I mean, it's not with the epsilon, but would be modified accordingly. And this has to be introduced here. I mean, this weak charge, this was the case of the standard model. So this is actually negative in the standard model. So if the new one basically cancel this and I mean gives the same amount but positive. So that's the way Exactly, it mimics, yeah.
Okay, so can you go back to 20?
Yeah.
Yeah, thank you. So there we see that, for instance, in the case where it mimics, you have the combination of liquid argon plus cesium iodide to match both of them, but not in the standard model case, right? Where it's 0. You see that actually the fit prefers the other one. So do you have an idea why this happens?
So for the liquid argon, actually, this is even more visible in the scalar and in the tensor, that actually the 0 is not the minimum.
Oh, there's a 0. Okay, yeah, I saw that.
It's
Sorry.
not the minimum, so you see, it's but
Yeah.
I mean, it's not significant, right? It's I think it's just the point is that liquid argon data have less statistics yet. I mean, the data are not, let's say, are not enough to really fit correctly to, I mean, so as I was saying, the significance that the significance of this result is not relevant. So, but in the liquid argon case, you see
it's not relevant, right? It's a very small effect. Yeah, I agree completely.
Also for the vector, indeed, the 0, the minimum is not exactly in 0. It's a bit shifted. Yeah.
Right. The interesting thing is that on the other side, it matches, right? It seems to match, at least. I don't.
Almost, yeah. It's slightly also shifted, but probably a bit less than the left side. Yes.
I see. So nothing to look forward to regarding.
No, I guess that with I mean, actually more data from this argon detector should come soon at some point, and I guess with more statistics, I mean, everything will be back to normal, I think.
Okay, thank you.
Okay, thank you, Joel, for the question. First of all, David Cardona says thank you for the answer, and I have a couple of questions. Maybe the details of the different measurements skip for me, but is there any possibility to see difference between the scattering if it is neutrino, antineutrino, depending on the source, or the experiment just see the both type of neutrino, they interact in the same way with the nuclei, or do you expect to have differences?
No, I mean, Coherent sees both of them, because in the flux that is used at Coherent, you have both neutrinos and the muon antineutrino. So yes, I mean, your question is more if the cross-section is different or
exactly.
Yeah, no, the cross-section is, if I remember correctly, there is a minor difference, which is not, because actually the cross-section which I gave here, well, this contains all the kinematics terms, but some of them are subdominant, so one can consider only the relevant ones. Yeah, no, the effect would be the same, basically. I mean, and these are taken into account. The coherency is the same, and the effect is this shift. It's the recoil energy that the experiment can see for both neutrinos and antineutrinos. Yeah.
Okay. So, and another question that when you were analyzing the case of light vector mediator, is any implication also that you can get for the case of scalar and pseudoscalar mediator, like actions, majorons, or I mean, not the standard majoron with a super weak coupling to the neutrino, but maybe other type of pseudoscalar particles, very light pseudoscalar particles?
Okay, so as I was saying before, the pseudoscalar in general is like the axial and leads to subleading interaction. So it's more complicated to see it. But in principle, of course, you could have a pseudoscalar mediator or an axial one. Is this what you refer to, or?
Yeah, exactly. You know, because when you were talking about this, I thought also about this experiment that they were measuring this. I mean, they were finding this fifth force that they. No, I don't remember the detail of the experiment, but it was a nuclear experiment in Hungary or something like that. And also they have the same, when they make the analysis for the different type of mediator, they take vectorial mediator and at most the scalar, because they were saying that the scalar, pseudoscalar and axial mediator, they were too difficult to try to extract because of the form factor and many other type of parameter and modelization that was beyond the scope of the experiment. So yeah, and the last question for me is there is other future experiment related with this, or the interplay with, for instance, with Dune experiment or other type of neutrino experiment, if they can join forces, let's say?
Yeah, there are some studies of so here there are many experiments which are running, and some of the blue ones are expected in the future. So experiments like Dune in general run at higher energies, but if you go to the low energy tail, then you could also observe some CEvNS events. So there are some people that have looked at that at the LBNF facility. Yeah, can be done, but in general, I mean, they explore a different energy range, so they are not really comparable in the sense that they are at, as I was saying before at the beginning, you need like you have like a maximum energy on the incoming neutrino to get this coherence of the process. So you see it's around 100 MeV. This depends on the target, but 100 MeV, it's already like kind of borderline, I would say. So of course, like experiments like Dune would be a much heavier energy. So you can use them, but only if you focus on the low energy tail.
Oh, okay. Thanks. And the one slide before, I guess, was the map. No, when you have the worldwide map. Okay. No, I was curious about this Violeta, because is it in Argentina? I don't know. It's just because of the map. I didn't know that it existed. Oh, I mean, this planet.
Yeah, I think yes.
Oh, cool. So let me check just if there are other questions in our social networks. Not. So if there are other questions from the people I mean, maybe Walter is gonna have some question, but they're gonna address it to you privately, Valentina.
Sure.
So let's, I mean, we are running out of time, but we thanks again, Valentina. It was very interesting, the webinar, and very, very complete. For sure, it's gonna be very helpful for many people that is gonna be watching it in our YouTube channel. And for the people that is following us, please don't forget to subscribe to the YouTube channel and our social network. And also don't forget to check out the Oscilador Armónico, this project that Valentina is participating on Outreach. And thanks, Valentina. Thanks to all the people that follow us. And we are going to see us again in a couple of weeks more with another law physics webinar. Thank you.
Thank you so much. Bye-bye.
Bye-bye. Okay, yeah.